In episode 107, titled Transfer Learning and Embeddings, Reuse, Fine-Tune, and Cold Start, we focus on how to reuse pre-trained knowledge so you can build effective models even when your labeled data is limited or your task spans a broad domain. Modern machine learning often succeeds not because every team trains from scratch, but because they start from models and representations that already encode useful structure. Transfer learning and embeddings are the practical mechanisms behind that reuse, and they help you move faster, reduce data requirements, and improve performance when training from zero would be expensive or unrealistic. The exam expects you to understand what transfer learning is, what embeddings are, and how choices like fine-tuning versus freezing layers affect overfitting risk and generalization. This topic also connects to operational realities like cold start, where you must make reasonable predictions for new items or new users before you have enough interaction data. The goal is to treat pre-trained representations as assets that must be governed, validated, and monitored, not as magic shortcuts. When you understand the trade-offs clearly, you can reuse knowledge responsibly rather than blindly. Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Transfer learning is the practice of reusing learned features or representations from one task, source domain, or dataset to help solve a different task in a target domain. The core idea is that many tasks share underlying structure, such as visual features in images or semantic patterns in language, and a model trained on a large, diverse dataset can learn general features that remain useful elsewhere. Instead of starting from random weights, you start from a model that already captures these general patterns, then adapt it to your specific task. This can improve performance and reduce the amount of labeled data you need because the model does not need to rediscover basic features from scratch. Transfer learning is therefore an efficiency strategy, using prior learned representations to reduce the learning burden on your smaller target dataset. It is especially valuable when training a large model from scratch would be too expensive in compute or data. At exam level, the key is recognizing transfer learning as reuse of learned features, followed by adaptation. Embeddings are dense vectors that represent meaning or similarity by placing items in a continuous space where distance and direction carry information. Instead of representing a word, product, user, or category as a sparse one-hot vector, an embedding represents it as a compact numeric vector learned from data. Items that appear in similar contexts or share similar behavior patterns tend to end up with similar embeddings, which makes them useful features for downstream models. In text, embeddings capture semantic similarity among tokens, while in recommendation settings, embeddings can capture similarity among products or users based on interaction patterns. The value is that embeddings provide a learned representation that can generalize, allowing models to treat unseen combinations more smoothly than they could with purely discrete indicators. Embeddings are also building blocks for larger models, especially transformers, where embeddings form the initial representation of tokens and positions. At an exam level, remembering that embeddings are learned dense representations that encode similarity is the key concept. Fine-tuning is the approach where you take a pre-trained model and continue training it on your target data so it adapts to your domain and task. Fine-tuning is most appropriate when you have enough labeled data to guide the adaptation and when your target domain has specific characteristics that the pre-trained model does not fully capture. For example, cybersecurity text, product catalogs, or specialized operational telemetry may use terminology and patterns that differ from the general data the model originally learned from. Fine-tuning allows the model to adjust its internal representations to better reflect those domain-specific patterns, improving performance on the target task. The risk is that fine-tuning can overfit if your dataset is small, causing the model to forget useful general features and memorize idiosyncrasies of the target sample. Fine-tuning also requires careful evaluation because improvements in training metrics can hide degradation in generalization if the adaptation becomes too aggressive. The exam expects you to treat fine-tuning as a powerful adaptation tool that requires sufficient data and disciplined validation. Freezing layers is the alternative strategy where you keep some portion of the pre-trained model fixed and train only a smaller set of parameters on top, often the final layers or a task-specific head. This is especially useful when data are scarce and overfitting risk is high, because it limits how much the model can change and preserves the general representations learned from the large source dataset. Freezing reduces compute cost as well because fewer parameters are being updated, and it often stabilizes training because the core feature extractor remains consistent. Conceptually, you are treating the pre-trained model as a fixed feature builder and only learning how to map those features to your target labels. This strategy works well when the source and target domains are similar enough that the pre-trained representations are already relevant. The trade is that freezing can limit ultimate performance if the target domain truly requires representation changes, because the fixed layers cannot adapt to new patterns. At exam level, the key is that freezing is a conservative approach for low data regimes to reduce overfitting risk. Cold start is a common operational problem where you must make predictions for new users, new products, or new entities that have little or no historical interaction data. In recommendation, for example, you may have no clicks or purchases for a new product, and for a new user, you may have no past preferences. Embeddings and content features provide a way to handle this because they allow you to represent new entities based on their attributes, text descriptions, categories, or other metadata rather than only on interaction history. A new product can be embedded using its description and category, allowing it to be placed near similar products even before it accumulates behavior signals. A new user can be represented through demographic or contextual features, or through early session behavior if available, providing an initial embedding that improves as more data arrives. This approach does not eliminate cold start entirely, but it provides a principled way to make informed initial predictions rather than defaulting to random or generic outputs. The practical point is that embeddings support generalization for unseen entities by leveraging similarity in content and context. Choosing embeddings depends on what you are embedding and what the downstream task needs, and practicing this mapping helps you answer scenario questions quickly. For text, token, or sentence embeddings capture semantic meaning, making them useful for classification, retrieval, and clustering. For products, embeddings can represent item similarity based on content attributes, purchase co-occurrence, or user interaction patterns, supporting recommendation and bundling decisions. For users, embeddings can represent preference profiles based on interaction histories, enabling personalized ranking, while acknowledging that privacy and governance requirements may constrain what user signals can be used. For categories, embeddings can represent relationships among groups and can reduce the brittleness of one-hot encodings when categories are many or hierarchical. The common thread is that embeddings turn discrete identifiers into continuous features that support similarity-based generalization. The exam-level competency is recognizing that embeddings can represent many entity types, not just words, and that the embedding source should match the signal you want to capture. Negative transfer is the risk that transferring from a source task that differs too much from the target can harm performance, because the reused representations may encode patterns that are irrelevant or misleading for the new problem. If the source domain is fundamentally different, the pre-trained model may focus on features that do not generalize, and fine-tuning may struggle to correct those biases with limited target data. Negative transfer can also occur when the source labels reflect a different concept than the target labels, leading the model to carry over the wrong decision boundaries. This risk is why transfer learning is not an automatic win, even though it often helps, because reuse only works when there is meaningful shared structure. Recognizing negative transfer requires paying attention to domain mismatch cues, such as different vocabulary, different data distributions, or different decision objectives. The disciplined response is to validate, not assume, and to consider freezing more layers or choosing a more appropriate pre-trained source when mismatch is suspected. At exam level, remembering that transfer can harm when tasks differ too much is an important guardrail. Validating transfer benefits must be done with holdout data rather than intuition, because pre-trained models can impress you with strong training behavior even when generalization does not improve. The correct test is whether transfer improves performance on a properly held-out evaluation set compared to a baseline trained without transfer or with a different transfer configuration. This validation should also check stability across folds or time splits when drift is likely, because transfer improvements can be fragile under distribution shift. It is also important to compare fine-tuning versus freezing under the same training budgets and evaluation procedures, because differences in compute and training duration can confound results. If you do not validate carefully, you may deploy a model that looks sophisticated but performs no better than a simpler baseline, or worse, that fails in edge cases. Transfer learning is an efficiency strategy, but it still requires disciplined measurement to confirm it is providing real value. At exam level, the safest principle is to validate relentlessly rather than trusting that pre-trained means better. Embeddings encode patterns, including bias, which means reuse introduces governance responsibilities that go beyond performance. If the source data contains demographic skews, harmful correlations, or historical inequities, embeddings can encode those patterns in their similarity structure and carry them into downstream models. This can manifest as biased ranking, biased classification, or unfair clustering that appears mathematically consistent but is socially or operationally unacceptable. It also means that embeddings can pick up proxies for sensitive attributes even when those attributes are not explicitly included. Communicating this clearly is important because it prevents stakeholders from treating embeddings as neutral mathematical objects. The professional stance is that embeddings are learned artifacts that reflect the data they were trained on, so they require bias checks and monitoring like any other model component. This is not a reason to avoid embeddings, but a reason to govern them.
Drift monitoring applies to embeddings because language, behavior, and context can change over time, making previously learned similarity structures less accurate.
In text, new terms emerge and old terms shift meaning, which can cause embeddings trained on older corpora to become stale.
In product and user embeddings, catalogs change, user preferences shift, and interaction patterns evolve, which can cause similarity neighborhoods to drift.
If embeddings degrade, downstream models can suffer because they rely on these representations as foundational features.
Monitoring can include tracking shifts in embedding distributions, changes in nearest neighbor relationships for key entities, and downstream performance degradation correlated with embedding age.
When drift is detected, you may need to refresh embeddings, retrain models, or adjust fine-tuning strategies.
Treating embeddings as living components rather than static assets is therefore part of responsible deployment.
This is especially important in adversarial environments where behavior shifts are intentional. Documentation of pre-trained sources and licensing constraints is a governance requirement because transfer learning involves external artifacts that may carry usage restrictions and compliance obligations. Documenting sources means recording what pre-trained model or embedding set was used, what data it was trained on if known, and what version was applied. Licensing constraints may determine whether a model can be used commercially, whether it can be redistributed, and what attribution or usage limits apply. Governance also includes documenting any fine-tuning performed, because fine-tuned models become new artifacts with their own behavior and potential compliance considerations. Without documentation, you cannot reliably reproduce results, audit model lineage, or respond to stakeholder questions about provenance. In regulated settings, provenance is not optional because decisions may need to be defended with evidence of how the model was built and what assumptions it inherits. Treating pre-trained assets as governed dependencies is part of mature machine learning practice.
The anchor memory for episode 107 is that you reuse representations, adapt carefully, and validate relentlessly. Reuse is the benefit because pre-trained representations reduce the need for massive labeled datasets.
Adapt carefully is the discipline because fine-tuning can overfit and freezing can underadapt, and the right balance depends on data quantity and domain mismatch. Validate relentlessly is the guardrail because transfer can help or harm, and only proper holdout evaluation tells you which is happening.
This anchor also implies governance responsibilities because reused representations can carry bias and licensing constraints that must be checked. When you remember this anchor, you treat transfer learning as a controlled engineering process rather than as a shortcut.
That mindset is what exam questions often probe because they want to see that you understand both benefits and risks.
To conclude episode 107, titled Transfer Learning and Embeddings, Reuse, Fine-Tune, and Cold Start, choose whether you would fine-tune or freeze for one scenario and justify it. Suppose you are building a text classifier for security incident tickets in a niche domain where you have limited labeled examples, but the language overlaps with general technical text. Freezing most pre-trained layers and training a lightweight task-specific head is a defensible choice because it leverages general language representations while reducing overfitting risk under scarce labels. If you later collect enough labeled tickets and you see the domain-specific terminology and patterns are not captured well, you can fine-tune more layers to adapt representations to your environment, validating the improvement on a holdout set. In a cold start recommendation scenario for new products, you would rely on content embeddings early to place new items near similar items before interaction data accumulates, then update embeddings as behavior signals grow. The justification in each case is the same: balance data quantity, domain specificity, and overfitting risk, and confirm benefits through disciplined evaluation. When you can state that choice and reasoning clearly, you demonstrate exam-level mastery of transfer learning trade-offs. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.